So now we can talk about the alkanes reactions. So before alkane reactions, so we already talk about the introductions, nomenclature, confirmations, physical properties, and different kinds of preparations. So there is the two important preparation was the roots reactions and Corey house synthesis. So now let's move on the new topic, the alkanes reactions. So we know this that typically we call the alkanes as paraffins because they are in carbon single bond, and this is sigma bond. So this is very strong. We can't break it easily. That's why alkanes are normally unreactive. That means they don't easily reactive with any other reagent. So that's why these are called paraffins. But they are also paraffins, but they can also react some reactions which are substitutions, combustion reactions in the typical condition. So there is the reaction of halogenation, combustion, and pyrolysis. Halogenation, combustion, and pyrolysis. Halogenation means we know that halogen are X, that means fluorine, chlorine, bromine, iodine. So if you add halogen in with this alkane, this is called the halogenations. So reaction of alkanes with chlorine, these mechanisms, and reaction of alkanes with other halogens, and then we discuss about the control of coordinations and coordination of other alkanes and factors that determine product distributions and selectivity of bromine. So now reaction of alkanes with halogens. So we know that in this alkane methane, if we separate hydrogen, so this is the methane, we will react with chlorine in the UV, that means ultraviolet spectroscopy, ultraviolet ray. So this will form the CH3Cl by replace with one hydrogen with the chlorine. So this will form methyl chloride plus hydrogen chloride. But this is a chain reaction, so that's why the CH3Cl also further react with chlorine. This will form CH2Cl, that CH2Cl2 plus HCl. So this is dichloromethane. But then another chlorination will be happened. So and another hydrogen will be replaced by chlorine. So CHCl3 plus HCl. This is called the chloroform. And then again finally this is CHCl3 finally react with the chlorine. So this will form CCl4 CCl4. So CCl4 plus HCl. So this is called tetrachloromethane or carbon tetrachloride. So there is a chain reactions behind the substitution of halogen in this alkane. So there is a mechanism behind it. First of all, halogen dissociations, step 1. So we see that in this halogen is a chlorine. So there is a influence of heat or lyse molecules. Chlorine dissociates its atoms, take one of the bonding electrons. So you know that chlorine is formed by sharing to their electrons with each other. So if they further take off their electron, so this will form the free radical of chlorine and free radical of chlorine. So and then the free radical attacked our main hydrocarbon alkane had the CH bond hydrogen. So we know that there is CH bond between carbon and hydrogen. So because there is a distribution of two electron between the carbon and hydrogen. So in this case the hydrogen will chlorine free radical attacked with this any hydrogen. So this there is also a bond destroy, bond broken. The electron keep with the hydrogen and the electron keep with the chlorine. So there is a create a methyl free radical. So this is the methyl free radical and also produce HCl, because in the hydrogen free radical plus chlorine free radical react with each other and combine to produce HCl. And we see that there is a methyl free radical produced, and here also a methyl free radical. So this will further attack with the next hydrogen. So this will form the dichloromethane, and then further react with the chlorine. So this is the chain terminations. Coupling of any two radicals complete the supply of reactive intermediates and terminates the chains. Several pairings are possible for radial coupling termination steps. So there is I think 4 steps for finally replace with all of the hydrogen with the chlorine. Replace all of the hydrogen with chlorine. So this is last finally from the carbon tetrachloride. So why do these reactions occur? Is the reactions favorable? So if this reaction is favorable, we can measure it by the delage, and so we know what is delage. Delage means the difference between energy put into the reactions and the energy given off from the reactions. If there is energy given off from the reaction is larger than the put in the reaction, so the delage will be negative, which is called the exothermic reactions. So in these exothermic reactions, the energy is high, so the reaction is favorable. But in the endothermic reactions, the given of energy is less than the put in the reaction energy, so the delage will be positive. So in this endothermic reaction, this is not energetically favorable. So here you see that there is a figure in this endothermic and exothermic reaction. So in this y-axis there is energy, and this x-axis there is reaction coordinate. So this is our reactant energy, and this is our product energy. Here you see that reactant energy is high, the product energy is low. So this is our exothermic, that means del is negative. But now if this is our reactant energy, and if there is a product energy is high, that means del is positive. This will be our endothermic reactions. So for endothermic reaction, energy is not favorable, but in exothermic reactions energy is favorable, more favorable. And also we can del is represented by the another formula, which is the difference between energy of bonds broken and the bonds formed. So here you see that there is CH bond is breaking, CH carbon hydrogen bond is breaking, and Cl bond is breaking. So the bond energy of carbon hydrogen breaking is 105, and then is 105 kilocalorie per mole. The chlorine bond breaking energy is 58 kilocalorie per mole. So here you see that also CCl bond is formation, which is 85, and ACl bond is formation, which is 103, that means 103 kilocalorie per mole. So now if we calculate the changes in enthalpy, we know that the bonds broken minus bonds formed. So this is the bonds broken minus bonds formed. So this is there we see that the delage is negative, that means this is the exothermic reactions. So the energetically the reaction is favorable. So why do methane and chlorine fail to react in the dark at 25 degrees Celsius? So we already say that for the previous the alkane substitutions with the halogens chlorine, so there must be the presence of ultraviolet ray, and the temperatures will be also high, more than 100, or I think is more. The more temperature high, the more reaction will occur easily. So but if we react in the dark place or dark environment, this will not work, this will fail to react. So why? The reason behind it. So the reason is, we see that in the carbon-carbon bond, here you see that in the chlorine is slowly divided with 2 chlorine, and the CCl4 is slowly divided. That means the flow free radical formation is slow. So that's why the reactions didn't occur or don't occur. In the absence of some external stimulus, only collision due to use of thermal motions of molecule can provide the energy added to the break the bonds at temperature below 100 degrees Celsius. It is very rare indeed that the thermal aggregations alone can supply sufficient energy to break the significant number. If the temperature is 100 below 100, there is the environment of the thermal aggregations can't supply sufficient energy to react to break this bond and to form the new bond. So because we know that the bond is stronger than more 30 to 35 kilocalorie per mole. So to break carbon hydrogen bonds of methane requires 104 kilocalorie per mole at 25 degrees Celsius, which again too much to gain by thermal agitation. So that's why there is no reaction will occur in the drug at 25 degrees Celsius. So here is some example of the enthalpy chlorination of methane energy changes. In this ester bond, there is energy changes del is equal to plus 243 kilojoule per mole. The free radical deviation is S2 the chain propagation. So the chlorine is chlorine free radical react with the methyl free radical, then replace the hydrogen with chlorine. This is from methyl chloride, and the chain terminations also react with then methyl chloride, then chloroform, then carbon tetrachloride from. So reaction of here you see that only the reaction with chlorine, but we know that there is another halogen fluorine chlorine with iodine. So the reaction of the halogen fluorine chlorine with iodine with methane show a wide spectrum of reactive activities. Fluorine is most reactive, is so reactive in fact that without a special precautions mixture fluorine and methane explode. So we can't use fluorine. And chlorine is the next most reactive. However, the chlorination of methane is easily controlled by the judicious control of heat, light and concentration. We can control the reactions of the substitutions. And again the bromine is much less reactive, so because of the size towards methane, and chlorine and iodine is so unreactive that for all practical purposes we can say that no reactions take places. So the reactivity halogens is most real, then chlorine, then bromine, then iodine. So the same order of reactivity holds for the reactions of the halogens with other alkanes and indeed with almost other organic compounds. The speed of reactivities is so great that only chlorination and bromination proceed at such rates to be generally useful. Then bond dissociation energy. So what is bond dissociation energy? So bond dissociation energy is defined energy required to break a particular bond into atoms. So I think our bond is carbon hydrogen bond. If we break this bond and separate these atoms, so those energy, how much energy we need, this is the bond dissociation energy. Then control of chlorination. We see that these chlorinations, we use methane plus chlorine, so this will form methyl chloride plus HCl. Then again this methyl chloride react with chlorine and this will form CH2Cl2. Then CH2Cl2 react with chlorine, then this will form chloroform. So at the beginning of the reactions there is only methane and chlorine is present. So chlorine react with methane and form methyl chloride. So here we see that there is reaction, however, yields methyl chloride, so that the reactions proceed, methane disappears and methyl chloride takes its place. So the production of methyl chloride is increased. So that's why chlorine attacks methyl chloride instead of methane. So that's why the methyl chloride will form methylene chloride, that means CH2Cl2. then the chlorine also further react with this HCl2 and form chloroform. So as the proportion of methyl chloride grows in the first step, it competes the methane for available chlorine. By the time the concentration of methyl chloride exceeds that of methane, chlorine is more likely to attack the methyl chloride than methane, and the second step, the chlorination becomes more important than the first. A large amount of methylene chloride is formed, which is similar way is chlorinated to chloroform, and it is in turn chlorinated to carbon tetrachloride. If you want to control this chlorination, so we can use the large amount of excess of methane. So in this case, event at the very end of the reactions, unreacted methane greatly exceeds methyl chloride. So chlorine is more likely to attack methane rather than the methyl chloride, and thus the first stage chlorination is the principal reactions. So because the great difference in the boiling point between the methane and the methyl chloride, we can separate these two separate these mixtures and more chlorine and but put through the process again.